Let's continue talking about the bivariate distribution now with an example. Imagine that we are rolling two dice. We have a dice has 6 different values. Then we can call the first dice as R, then the second dice as C. As you can see, a dice is simulated using a multinomial, and then we simulate 10,000 events, and for the other variable or for the other dice we also simulate 10,000 events, and then the pair is computed like this one, is stored in a list, which is C, and then we can use that to compute the bivariate distribution, which is the probability of the random variable xr and the random variables xc. The bivariate distribution is estimated like this one. We just go for all the elements that we have sampled, and then you just count them and sum, and as we can see, this part is n, and the output of that one is, we can see the output of the bivariate distribution. Remember that the marginal can be computed using this matrix, and the marginal for this one, the marginal for this one I didn't write it down, but it's just going to do it quickly, which is the sum for all the computing the rows. So it's the sum for all the C's. That's the formula for computing the marginal. So that's what it is computed in this line that I'm going to run once I can do it. So that's the marginal, and we are seeing the outcome of that. And as you can see, is quite the marginal is 1/6. So it is what we expect it to be. The marginal for the other one, well, it's computed if one is computed with the x1, the other one is computed with the x0, and then if we assume that these two variables are independent, then the bivariate distribution of two independent variables is computed as follows: just the product, and the product can be obtained using the dot product between the dot product between the two matrices. One is going to be a column matrix, a matrix with just one column, and the other is going to be a matrix with just one row. And well, this is the output. If we remember, I think we have seen W, and we see int. They are very similar, and if they are, I mean, if these all the different outcomes of the experiment of the random variables are independent, then the subtraction between the estimated bivariate distribution and the one bivariate distribution assuming independence, which is which is expressed in this formula, can be expressed as W minus int. Well, it's going to be close to 0, and well, it's not 0, but all the elements are kind of close to 0. Now, what happens if we don't have two independent random variables? Let's make a dependence in one of the values, and the dependence is going to be introduced with this if. We are doing exactly the same as the previous example. The difference is that when R and C are equal, meaning that both dice have the same value, so they are both 0, they are both 1, both 2, and so on, we are going to discard that sample from our, I mean, we have that sample, but then we are going to assume that the process that we are simulating discard those dices that have the same value, or discard those events. Now, if we follow the previous step, what we have is that the difference between the bivariate distribution, the estimated bivariate distribution, and the bivariate distribution as obtained by the assumption that these two random variables are independent is the following, is the one that is shown here, and we can see that the diagonal has higher values than the rest of the matrix, indicating that for those items, for those pairs, there is a dependency. We can go a little bit further and make a procedure where there is a dependency, and the dependency is expressed in this part. Let me just go a little bit. So we are going to say that the row is 2 if the column is 1 and there is a random variable with a very low probability. We sample a random variable from 0 to 1, and if that random number is less than 0.1, so which is going to happen on pretty much the 10% of the time, we are going to say that C is 1, and so the columns are 1, the column is 1, and the row is 2 in this simulated example. Performing the previous steps, we can see that we can compute the difference between the bivariate, this estimated bivariate distribution, and the one obtained assuming independence, and we can see here that, well, kind of all the elements are 0, close to 0, except the one that it is in the column 2, which is the row 2, which is the third row, because remember that 0 is the first row, 1 is the second one, and 2 is the third one, and on the second column. And the value that I'm looking at is 0.1, it's 0.0106. And as you can see, that's a value that is higher than the rest of it, which implies that there is a dependency on that value. Well, for now, I'm going to make a brief summary of everything that I have been talking about, which is we have described how to estimate a bivariate distribution. Then we know that if we have a bivariate distribution, we can compute the marginals using the marginals, and assuming that the variables are independent, then we can build again the bivariate distribution. So if that distribution, the one that we build later and the one that we estimated using the samples, if that distributions are kind of similar, then the variables are independent. But if they are not similar, there are going to be some elements inside that matrix that are going to be non-zero, and those elements indicate where the dependency is. We are going to continue talking about this in the next session, but now talking about we are going to use another example that it's more that are bigrams instead of rolling 2 dice.